Okay, so I believe this question was something like for what polynomials with real coefficients? So you have P and Q are real polynomials. They satisfy P of Q of X cubed equals X P of X times Q of X cubed. So this is kind of like it's almost like an exercise. If you know what polynomials are, this is not too big a problem, and then the rest is just kind of computations. There was one thing I tried to do that was kind of interesting that I'm not sure if it would really. I don't know if it helps you solve the problem any nicer, but it was kind of interesting. You could let x be like a root of q, and then you have that the constant term of p is 0. And so this is a bit of an aside, okay? So you let x equals a root of q. And then you have that p of 0 equals 0. And so if p is like some polynomial like a n x to the n plus a1x plus the a0 now be 0, so it would be just like that. So then p of q of x cubed is just equal to an q of x. To the 3n, so plus a1 q of x cubed, and that's supposed to equal x p of x q of x cubed. And then you can kind of cancel out a q of x cubed to get an q of x 3 to the n. This is probably not how you should try to solve this problem, but this was just something I don't know, naturally came up. So minus 3 plus a1 equals, and of course the a sub i's are all real numbers because of this. So this is equal to x p of x. Okay. And if you put that in, you get a n x to the n plus 1 plus a1 x squared. Yeah. So if you wanted to go from here and just trying to see what's wrong with this, or what could be said about this, I guess the kind of thing is you might end up just saying something you would have said anyway without doing all this. I don't know, you might think it gives you an easier way to figure out what Q is. See, the problem here is, Q is to the power of 3n minus 3, and here the x is only to the power of n plus 1. So n has to be a pretty small number for that to work. And that's assuming that Q doesn't already do something. So you might actually notice that if Q was the identity, then P of X was squaring. So P is squaring and Q is the identity, that would work. So if Q didn't have any powers in it, then N would have to be 2. Q does have powers in it, so if Q was like 2, degree 2, then it would be 2 times 3n minus 3 equals n plus 1, which is, so that would make n equals to 1. No, that doesn't work, so just have to be 5n equals 7. Yeah, so it doesn't quite work. N minus 1 equals 3 plus 1. Yeah, I guess that's the problem. You put the m here, you get 3m minus 1n is equal to 3m plus 1. Yeah, okay, but I don't know. So if you can get some nice thing from here, I would think it's interesting. But I guess the problem is kind of just too trivial. So um basically if you look at the on the left-hand side, if you think about degrees, okay, so maybe we can prove some of these things by request. So if you look at the degrees, P of Q of X cubed equals X P of X Q of X cubed. So the way degrees work is, let's see. So if you have like f of x equals like a n x to the n plus so on, this a n is not 0, then the degree of f is equal to n. So yeah, this is less of a problem than almost more of an exercise in polynomials. So the degree of f is said to be n. Okay, so that's basically easy for everything. So you have constant polynomials is just a0. Then you have degree of f is equal to 0. Okay. If you have any higher powers, then the definition works. So the only problem is what happens if f of x actually equals to, so this is non-zero because of this part of the thing. What if f of x actually equals 0 for all x? It's a 0 polynomial. Then the degree is defined to be, it's kind of, it's defined to be negative infinity. Okay. So it's more of a memory aid than anything else. So I can't take any positive values. And I guess maybe this definition will make sense when we do some of the rules, yeah? So if you have two polynomials multiplied together, so f of x times g of x, yeah, equals, so what's the degree? That's the kind of question we're trying to ask here. Xn, that's the f part. What if the b part was the bn, bm? So the degree of yeah. So if it's nice, if bm is not 0, then the degree of g is just m. Okay, the degree of g is m, and you can see when you multiply two non-zero things, it'll still be non-zero. So you get this is equal to a n bm x to the m plus dot dot dot. Okay. I'll look at the chat for some questions in some moment, but so this clearly says that degree of fg is equal to the degree of f plus degree of g, yeah? Okay, but that doesn't cover all the cases, because then you have, what if f and g were, I guess the only special cases that makes this anything other than trivial is, can people type if they hear me? If someone type yes, we can hear you. Anyway, so the thing that's making this other than trivial is the possibility that g or f is a zero polynomial, okay? So if either of them is 0, the degree is negative infinity. So we have to have some kind of multiplication rule that says like n plus negative infinity equals negative infinity, right? And that's probably why you define it to be negative infinity, because then you can see that negative infinity plus any number is still negative infinity in sort of a heuristic sense, at least. So because any zero polynomial times any other polynomial is a zero polynomial, okay? So maybe this is one of the good motivations for why to define the degree of a zero polynomial to be minus infinity. But nonetheless, it's just a symbol that has to obey those addition rules, right? So that the rules are nice no matter what the polynomial is. Oh, I'm starting to look at the chat. Sorry. We can't see past the QN 3N. Second dot is the limit of the board. Ah, you can hear me. The current board is within the screen, I think. Yeah, it says non-constant polynomial. Cool. So can people see the screen now? Let's see this. Oh, okay, cool. Okay, so so for example, now we know that the degree of q cubed, the degree of q cubed is equal to 3m. Let's the degree of q be m, okay? Degree of t equals n. So the degree of the right-hand side, we know it's 1 plus n plus 3m. Yeah. Okay. Okay, then the other thing is the composition. Let's have a look at compositions. How does compositions work? So if you do compositions, F composed with G, G composed with F, you have like AN and then it's like G of X to the N plus. Yeah, so if they're not the zero polynomial, then the degree is pretty straightforward. It's going to be just m times n, right? Because this is not zero, and the thing in front of the g is not zero. Okay, so then in this case, the degree of f composed with g is equal to mn. What if you have a zero polynomial? What happens there? Does the rule make sense? So if f is the zero polynomial, then so composition is not commutative. You have to do it both ways. So if f is the zero polynomial, then the composition is just zero, right? And you can maybe think of that as still m times n, with m being negative infinity. Okay, but what if g was the zero polynomial? So if g is a zero polynomial, so what if the thing on the inside is the zero? So then you just get f of 0 is equal to a0. And then the degree is equal to just 0. Let me write that again. So I want to know what happens if you have degree. What happens if you have sort of 0 of g of x? So that equals 0, obviously. And then you have also f of 0, which equals a0. So this is trying to say, I guess, that if it's just the product, it should be the negative infinity times n equals negative infinity. Okay. This one, what's this one saying? So if f is non-zero, well, obviously negative infinity times negative infinity should equal well, that's the problem, isn't it? That shouldn't equal negative infinity, but it does. Okay. And then what if f is non-zero? Well then, see, it might not be the zero polynomial, but the constant term could still be zero. If the constant term is non-zero, then the degree is just zero. What's that saying? So this is pretty bad for this rule. The degree of, yeah, I mean the problem says it's non-constant, so we don't need to know about that for this problem. But there are, yeah, these exceptions are hidden in here. So the degree of f is not negative infinity. So let's say it's n. Then you have n times negative infinity. So if you times it this way, according to this rule, you get either 0 or negative infinity. Depending on whether the constant term of f is 0 or not. Yeah. So if f was a constant polynomial, then you'd get 0 times negative infinity is equal to 0. Some higher degree, then it's n times negative infinity is equal to possibly negative infinity. And if the constant term is non-zero, then it's, yeah. So it's actually quite a bit of a mess. So it's probably better just to um just keep in mind that, when the polynomial is 0, the degree rules might need some exceptions. Okay. And so if you know that that's how composition works, and because we know that Q is not a constant and P is not a constant, then the degree here will be n times 3m. Okay. Composition of 2, 0. Yeah. This rule looks pretty strange for that, yeah. Yeah. So then you might want to see you could use that as an argument for saying that the zero polynomial should be positive infinity degree. But then people might complain in other ways. Okay, so yeah. Yeah, so the other way might be more explicit and gives you more of an idea that polynomials have to be small. But look, you have 3nm has to equal 1 plus n plus 3m. So this is already it's hard for this to happen, right? Um, yeah, it's actually amazing I got the internet to work. I actually didn't get the internet to work. Nothing it works except so apparently my dad has a hotspot with Telstra instead of Vodafone. The Vodafone didn't work, the internet didn't work. The Telstra one worked. Okay, so yeah, so this is maybe actually this is actually relevant to the next thing we're talking about. So that's kind of interesting. Yeah, so these are all like so they're not constant polynomials. So these are all actually positive integers, yeah. Yeah, and it's really hard for this to be true for positive integers. Hmm. How do we do it? Maybe we could do like 3m outside of n minus 1 is equal to n plus 1. So that makes it look pretty ridiculous. So if you're timesing something by 3m, it has the net result of adding 2 to it. So that has to be a very small number. So clearly 2 and 1 work. N equals 2, n equals 1 works. If n was bigger than 2, you get 2 goes to 4 after timesing by 3. Yeah, I'm pretty sure this is the limit of what works. So then you basically have p of x equals ax squared. I'll use a2x squared plus a1x plus a0. Though we kind of know what we know a0 is 0 that from before, so that could help. Q of x equals, and we can write bx, b1x plus b0. Oh, I see. This could still be quite a trek, huh? Even knowing that. So maybe the other approach did help a little bit. So using the other approach, what would you get? You get a2 a2 q of x cubed. So you get b1 x plus b0 cubed plus a1 equals x times a2x squared plus a1x. So maybe the other stuff wasn't a total waste of time. It does save some computations. Um, oh yeah, by the way, if people want to present some solutions, I'm more than happy to oblige. Um, I, um, yeah, so yeah, and I guess the you know the obviously the ones people are interested are in some sense more valuable. Okay, so what's going on here? Yeah, so we can do a bunch of stuff, I guess. We can equate the coefficients of x cubed. So we got b1 cubed equals 1, yeah? So that's good. Um, to get the constant term, we have a2 times b naught cubed plus a1 equals 0. That's, so this thing doesn't tell us anything about a2. Oh, okay, it does. So the a2 does survive into the cube. So if we equate x squared, we have a1 equals, I don't know, it's really weird. I guess this problem could be psychologically quite damaging if you just kept thinking it was trivial and you couldn't get it. Because that's how I would approach this question. Just keep thinking it's trivial and then like um maybe have some bad things happen for being too overconfident. So a1 equals a2 times 3 times b1 squared times b0. Is that right? Hmm. So maybe something we didn't do is the coefficient of x, because that's also 0. Coefficient of x is also 0. So that's a2, b1, 3. But that's going to get something for sure. Yeah, so that's a big one, because that's going to give you... Okay, so we know b1 is not 0, so either a2 or b0 is 0. Is that how they do question ones up in Greece, huh? So a2 could be 0. If a2 is 0, then a1 is 0, which makes p constant, so a2 can't be 0. So then b0 has to be 0. And then a1 has to be 0. So what's the conclusion then? Conclusion is, don't just think problems are trivial. Oh. Yeah, I guess what you can think of, maybe one way to think of it is, the problem could be a test of your problem solving ability. And or it could be a test of your proofwriting ability. Okay, so this question, I think, is a test of your proofwriting ability. So the problem-solving part is trivial, but to get through it all without losing marks, well, um, there's a certain challenge to it. So what did we conclude? B0 is 0, so Q of x is equal to x. P of x is equal to oh, this one also gives you a1 equals 0, yeah. So a2 doesn't seem to be, so it's just like a parameter that stays in there. And what about a0? A0. Oh, we already know a0 is 0. Yeah, so then p is just a constant times x squared. Qx is equal to x. And I think we can see that they work. So this gives you ax to the 6. And this gives you ax to the 6. Yeah. Okay, well. It didn't take long and none of it was hard, but probably longer than you expected, yeah. Good exercise in polynomials if you haven't done them before. I think. I guess this is also on the HSC syllabus too, so parts of it anyway.